Okay, I think, first of all, Ms. Sara Carniello, thank you very much for accepting our invitation to contribute to this Emerge school. I will just introduce yourself in the audience. So, Ms. Sara Carniello is coming from Joannem Research Center, in Austria. The webinar will be about life cycle assessments for printed electronics. That is following the previous also webinar today. It's a very important activity for emerging technologies. So in this webinar, the speaker will discuss how to read or translate LCA results and how to adopt life cycle thinking in technology development. That is very important for Europe and I think many regions of the world to address this electronic waste due to this development in electronics and beyond. So a few words about the speaker. So Ms. Sara Carniello worked many years in the semiconductor industry before joining Joannem Research in 2022. In her current position, she models the environmental impacts of technologies with a focus on electronics and advanced materials. She holds a master in materials engineering from the University of Padova and an MBA from the Leuven. This is university from Leuven, I guess, in Austria.
Leuven, yeah.
So thank you very much. So the floor is yours.
Thank you very much for the invitation. It's a pleasure to discuss once more this topic of sustainability in electronics and more specifically in print electronics. I see there is a growing attention for this topic because I also get invitations more and more to talk about it and discuss about it, and it's really nice. The presentation will be in two main parts. The first, say 20 minutes, will be dedicated in general to the sustainability aspects that we might meet in print electronics. So just to contextualize a bit why we need to care and what are the main topics you need to watch and to have in mind when you do some development. And the second part is dedicated more to the life cycle assessment, but really from the perspective of a technical team that wants to integrate the results or wants to learn from the life cycle assessment how to make more sustainable products. So it will be a very general introduction to the method to put you in a position to understand especially the results and learn out of them. So before we enter the topic of electronics, in case someone has still some doubts that we have an issue with climate and with environmental damage in general, just two diagrams. The one on the left here is the emissions, or are the emissions, the climate, the greenhouse gas emissions, and you see different curves. Sorry?
There is a background.
Okay. Do you see my mouse?
Yes.
Or do I need? Okay. So here you see the current emission curve where we are currently, and this green one would be the emission curve where we should be if we want to stick to this commitment and limit the warming to 1.5 degrees. So you see there is a huge gap between what we are doing now and what we should be doing now. And since most of us are active in the material science and in materials engineering, where we could say that more or less 40% of these emissions are related to the materials, so to their extraction, to their working and processing and transportation. So materials are a very powerful lever we might have to reduce these emissions. And on the right side, it's an even more interesting plot It's a bit maybe not so immediate, but you see on the x-axis the Human Development Index. And this index is made up of different social and political and environmental parameters. So it gives a kind of quality of life in a country. And in the y-axis, you see the environmental footprint. Here it could be in hectares per person, but anyway, I think this is in the planets that we would need, number of planets that we would need to keep this quality. And the points are the countries. So to bring it to the point, if we want to have a nice quality of life, we should be on the right side of this line. If we want to have a sustainable way of life, we should be below this horizontal line here. So we should be in this quarter here, so in this portion of the plot. And as you see clearly, there is no country in the world achieving this at the moment. Either the quality of life is really poor, or the quality of life is high, as it is in our countries, but the consumption is way too high. And you see a kind of exponential dependency of the environmental impacts in general on the quality of life. And if you take as a y-axis the production of waste or the use of plastics or the use of raw materials in general, they have more or less all the same trend. So to improve a bit our quality of life, we need to increase a lot the consumption of resources. And this is what we should try now to break with the new developments and with the new also economical models. So we have clearly issues here, and we all want to be active, but maybe many of us will also hear this question. No? So the chips are so small, electronic devices are so small, why do we need to care? We must also say, referring to conventional electronics, so silicon-based electronics, that with improving technology, so with smaller technology nodes, the consumption during the use phase is decreasing. And at the same time, the consumption pro device, so really pro chip in the production is also decreasing. But as a general rule, the importance of manufacturing increases. And this is clearly shown here in this plot, where you see different electronic devices from wearable to smartphones to computers. Some of them battery operated, some of them always connected. And you see that these red columns here, they are gaining importance, especially in the battery operated devices. That means that if we want to really say to know what are the resources that a device is consuming, you cannot look simply at the energy consumption during use, and you must ask yourself questions also over the whole life cycle. So this is certainly a key aspect of electronics. So in general, again, maybe referred to electronics in general, not only print electronics. Electronics is seen as considered an enabling technology. That means that it's also thanks to electronics if we can go for e-mobility, if we have an energy transformation towards renewable energies, if we can improve our production. In this sense, is an enabling technology for the transformation to a sustainable and just economy, as the EU Green Deal says. And also, maybe it's not so a side note, because of its enabling role, you can also quantify some investments in electronics as a sustainable investments under certain circumstances. On the other side, there is a negative impact of electronics, and this is what we need to keep in mind when we develop the new technologies. First of all, electronics in general has a very high energy and material consumption. And this is certainly true for conventional electronics, for silicon-based or also 3-5 electronics. It is better, I can't spoiler, also for print electronics, but still is an issue. And this energy and material consumption is not clear, it's not visible if you see only the device itself, because they are so small. And because most of the materials that you use to fabricate them do not end up in the product. And they are auxiliary materials. They are resins for the masks. They are solvents or gases for implants. They are removed after production. So you need a life cycle perspective. The other point is, for example, so the critical raw materials for conventional electronics. More than half of the materials on this list are used in electronics. So there is no electronic product doing without critical materials, and this is an issue, not only for the environment, but even more an economical issue. And the last point is that recycling is very complex, and even if you read 17% of recycling, this is actually limited to the larger components of electronics, to cable or maybe some PCB or some devices, but most of the materials are actually lost. So there is no closing the loop yet in electronics. So when I do my analysis in general in electronic products, I consider these aspects for the environment. And what are these six aspects? 5 of them, so the green ones, they come from the European goals, environmental goals. So the EU Commission defined 6 areas where Europe needs to be more sustainable. And the 6 areas are climate change mitigation, climate change adaptation, which is not in this list, circularity, pollution, water consumption, and biodiversity. If you want to claim that your product is sustainable, you need to prove that you improve at least one of these topics and you don't damage the others. So this is related to the probably known taxonomy. If you want, also in the near future, if you want to have some funding projects, also they will follow this logic. So there is no research topic today that can ignore these topics in general. And there is one in gray, you see, the supply of critical materials. I added it to this list because, as I said, at least for conventional electronics, it is a very important factor. You also see maybe that biodiversity is not that highlighted as the others. And the reason is that, at least in the electronics or in many cases, biodiversity is also a consequence of the others. Now, if you have pollution, if you have some dispersion of I don't know, radioactive materials or polluting materials in the water or something like this, of course, you will impact biodiversity. And if you have large emissions and you will change maybe the temperature or you will change the acidity of the water in the sea, then you will have an impact on biodiversity. So it's a kind of, say, indirect impact in most of the cases. So before we enter really the topic of life cycle assessments, I would like to compare briefly the issues of conventional electronics and the potential benefits that we might have using print electronics, or maybe the drawbacks that print electronics has. What you see here is a very high-level summary of the emissions related to conventional electronics. So looking at the right side of the slide, this is taken from a very general report from McKinsey, where they looked at different fabs. You know, also in conventional electronics, the processes are more or less the same, so there is no large difference from fab to fab. And these are the total emissions. And what are the reasons? What are the causes for these emissions? Scope 1 emissions are the emissions really occurring on site, so within the factory boundaries. They are due maybe to heating or to burning gas, but in the electronics, they are mostly due to fluorine-based compounds. And they are used in conventional electronics for etching. And you see there are also these gases. And because conventional electronics makes a large use of high temperatures, they are used as a chilling fluids. So where there is a high temperature, there is also, of course, cooling, and there you have a leakage of fluorine-based compounds. And this makes up a fairly large portion of the emissions in conventional electronics. But the largest part is related to the scope 2. That means there are emissions related to energy consumptions, but they occur somewhere else. So they are the typical emissions for the electricity production. And here you see two main parts. One is due to the infrastructure, to the clean room. It's making up 30 to 40% of the total emissions. So it's really a huge part of the emissions for conventional electronics. The other part is due to the tools, because as you might know, conventional electronics, you have high temperature, you have deposition that might happen also at high temperature, you have the diffusion ovens, and you have plasma treatments in a lot of steps. So you need really a high energy during the consumption, the production. And the last point, the so-called scope 3, this is due to the supply chain. And in this case, it's only the upstream, so raw materials. And here, a fairly large amount is due to the raw materials employed in the production, because they are high purity chemicals, because they are monocrystalline substrates, because you need gas, so high purity gas, you need targets for physical deposition, and you need precursors of different kinds for the chemical deposition. So they are also one of the largest contributions for the overall emissions. But this is conventional electronics. And here we want to talk about also print electronics. So can it be an improvement, print electronics? Going from topic to topic, the high energy processes, they are certainly better in print electronics, and we don't have high temperatures. We don't have a lot of gaseous treatments that also need management of gases. We don't have plasma, or have very limited application of plasma. Infrastructure, yes, we have clean room, but it's not as demanding as conventional electronics. And also, not to forget, is there is no gas or almost no gas treatment, whereas in electronics, so in conventional electronics, you have a very large implants or plants just for managing the gases, which are potentially also toxic. And you have high purity materials, yes, but we don't have usually the monocrystalline materials. And once again, they are not in gas form in most cases. So they are simpler to manage. And there is no etching, so we don't have this fluorine-based chemistry. But there are some fluorine-based chemistry in the products, maybe as an active layer or as a non-sticking coatings. So we might have something, and there is a clear difference to conventional electronics. These fluorine-based materials are part of the products, so they go really out in the world, so to say. And if we talk about pollution, what are now, in a nutshell, the potential issues in conventional electronics and in print electronics? In conventional electronics, you have, again, the chilling fluids, so based on fluorine usually. You will have some wet chemistry related to resist and to cleaning, the CMP slurry, and you will have a lot of gases. Whereas in print electronics, you might have solvents, toxic or non-toxic. You might have other organic chemicals, also fluorine-based, but they are usually wet chemicals, so they are simpler to manage, and they are safer, at least because they are liquid, so the risk of leaks and of contamination that they are difficult to manage, it's a bit lower. But there is one key difference. Most of these chemicals remain in the product and go out and have a use phase and also have a disposal phase. So when you do this the analysis of the SEA analysis, you must keep in mind when you develop your scenarios also, you must ask the question, what happens with these chemicals during use and during disposal? What happens, for example, under UV radiation or high temperature or high humidity? Will they degrade? Will they go into the environment? Will they stay in the product? Whereas in the conventional electronics, you have usually a very nice bunch or a solid block of mostly inorganic chemicals and inorganic elements, and there is basically no dispersion once this chip is out in the environment. One point also that it's worth mentioning is the water consumption, which is something that would not associate to electronics in general, but everywhere where you have a high energy consumption, you will have a high water consumption for the energy production on one side and for the cooling on the other side, and also for the emission abatement, so for the treatment of the emissions from the site. So this is taken from TSMC, so the largest foundry in the world. From their environmental report, they say they have 13 plants, treatment plants for different wastewater. So it's a really complex and demanding, say, infrastructure that you need to have. And in print electronics, because you don't have this high energy consumption, you have less water consumption upstream for the energy production, and you have also less water consumption for the emission abatement, and less water consumption for cooling, because you don't need to cool down from this high temperature as in the conventional electronics. But you still have wet solutions to manage and treat, and potentially you have even more wet solutions than in the conventional electronics. So you will have maybe less water consumption, but it might even increase in the complexity. A few words about critical raw materials. A definition, in case you don't know the definition and why it is more actually an economic topic than an environmental topic. These raw materials are fundamental for strategic technologies. Strategic technologies are electronics, they are the electrical mobility, aerospace, batteries of all kinds, robotics, and the like. Their demand is increasing fast, and their supply is at risk. Either they are scarce, so they are really difficult to find, or they are in the hands of few countries. So Europe is vulnerable in this sense. And if you see this list, there are quite a few materials which are very important for conventional electronics. And on the other side, in print electronics, most of the cases you have none of these materials. And print electronics simply offer alternative solutions to fulfill the same function. So this is a clear advantage of print electronics compared to conventional. For the circular economy in general, circular economy means you want to maintain the value of the products and materials as high as possible for as long as possible. And you have different strategies available. And one strategy is, for example, to improve your efficiency, to use less resources for the same output. And this is something that certainly in the electronics in general is occurring as much as possible, just because resources are so expensive. Then you have the strategy of use longer the products, but it's something that you cannot really control usually, because you provide your device, but you have no control on the use phase of the final product. So you can just make your devices durable and reliable, but if at the end of the day this will translate in a longer use, it's outside your control. Then, of course, you have the option to recycle, no? Which is usually the first thing you connect to circular economy. The problem of many, especially conventional electronic dies, they are monolithic. So it's very difficult to separate the part or disassembly the parts later. And in general, you have really small quantities. And if you have large quantities, they are so spread in the world that it's difficult to bring them together and really make a nice, say, volumes to have efficient processes. And you have another option, which is the regenerate. That means bring back into nature. And this is what you can achieve if you use, for example, with bio-based and even better biodegradable polymers. So this is an option, at least for some applications. What is the problem of conventional electronics is really the concept in itself. So without going through all the numbers, to make one monolithic silicon wafer, you need a huge amount of resources. And what do you do now then when you have one wafer? You fabricate your chips, and actually you use usually 700 micrometers or 779 micrometer thick wafer, and then you grind away most of the wafer because it was just there for mechanical purposes. And if you think really what is used as a semiconductor material of this silicon, actually it's only maybe the top 20 micrometers of the silicon. The 750 micrometers below this, they are there and they were very demanding in their fabrication, but they are not used for their function. So it's a kind of waste of high quality material. And this is what print electronics is trying to solve, because with this additive approach, print electronics try to bring the materials only where they are really needed, only as much as they are needed. Yeah, so it's really a different philosophy, I would even say. So it's a fit for purpose. So with additive manufacturing, you can fabricate what you need and not more. But we all know there are a lot of challenges related to this. The electrical properties are not comparable with silicon, so we usually end up with very large devices, also because the resolution is not comparable with the other processes. So we have let's say very effective materials with a low environmental footprint, but we need much more material than for conventional electronics. So the balance is not that clear in favor of print electronics, as it would be comparing, I don't know, just a square centimeter, for example. And there is also another topic in additive manufacturing. When you have organic chemicals, you might end up with a shorter lifetime. So you must be careful to compare really the same functionalities. So I'm speeding up a bit. Just in a nutshell, maybe the comparison between the two. When you compare devices, you have certainly the topic of the size for the print electronics and of the fact that you have chemicals inside your print electronics devices. Whereas in a conventional electronics, you have usually, let's say, harmless anorganic chemicals. But if you stay at PCB level, the size is less a topic because also with print technologies, you can reach, say, conventional, more or less, because it's comparable to conventional technologies. And also the leap or the gap to the established processes is in many cases not that high, that large. So you might have lower entry barriers for print technologies here. But here, what I personally see as the largest benefit is that with printed PCBs, you might have recyclable PCBs and recyclable with really efficient processes. So you might have really increase the recyclability of PCBs. So coming to the second part of my talk, how can you use the LCA and what is an LCA in the first place in your technical work? So when I measure, or I have to measure the environmental impacts, or to model the environmental impacts, to be more correct, I usually consider these categories. So, of course, the emissions into air, the depletion of resources, also including water, and if we have enough information, also the toxicity, which is a bit a tricky part. And if also circularity is a topic, then we take care also, or we look into the source of the input materials, not only from an environmental point of view, but really also recycling rate and the like. And we also look into the fate, so what happens at the end of life, and the economic value. So that if we need to choose between recycling one material or the other, then we have also the economic perspective inside. Why do you need it at an early stage? Because as everything else, the earlier you make these assessments, the more freedom you have to improve. So it's always the same plot. If you talk about costs, if you talk about environmental impacts or functionalities, the earlier you know it, the more you can make it. So life cycle thinking. I mentioned already, sometimes you need to adopt life cycle perspective. And what is this life cycle perspective? It means that you take your technology or your material and you put it into the product and you try to follow this product in all the life stages. So from raw material extraction to part manufacturing to full assembly, use and disposal and recycling. And this means that you need to adopt a systemic view on the topic. It's not only your material, but you really need to expand your view. And it's also a multidimensional problem because you need to care not only for the technical performance, but you also need to care for the environmental performance, for the economical parameters, and ideally also for the social impact. So you need to have to consider different perspectives. And this is usually how people react when they start doing this. So it's a kind of loss in the mess. Because it's systemic and it's complex, it means you have a lot of variables and they are correlated. So if you tune one, you will also move other variables without wanting it. So you will never have a clear solution or a best solution. You will always have to find the optimum, say, system in general. Very important aspect of this life cycle thinking demands the sharing of information and data. It means you are not working alone in your lab or in your company, that you will need information about what you receive as input, and you will also need to take care of what happens once these things, be it waste or be it product, will go out. So you need to share and you need to get information. And the very last point is when you see assessments, when you see environmental impacts, they are always based on models and on databases. But the idea is it's really an abstract model. It's not measured. So it's something based on research based on huge data inputs, outputs, and so on. But it's an abstract model. The importance of life cycle thinking. I put here one example related to the piezoelectric material, this PZT, so the lead silicon titanate. Lead is not so desired today. It's on the ban list for Europe, with exception for PZT, but it's very difficult. Companies don't want to work with lead at the end of the day. So there is a lot of work going on searching for alternatives. And here I report 2 alternative materials. It's taken from a publication you see here. Of course, using the life cycle perspective. And they are on the paper, both of these alternatives, they are less hazardous than lead, because they don't have lead. They have niob and potassium and natrium, and here it's natrium, bismuth, and titan. So this should be safer. But in a life cycle perspective, and this is really toxicity, you see there's this KNNN. So this option has a very large impact, much larger than the PZT, which you want to replace. And why this? Because niobium comes from usually radioactive minerals. So you have a lot of chemistry to take out niobium, and you have also radioactive waste. So you have upstream huge environmental impact that at the end of the day makes your overall material worse than what you want to replace. So it's something you should always have in mind, that it's not only what you see in the material, but it's also what happened before and what might happen later. So life cycle assessment as a method itself. What is the relation between assessment and the thinking that I was explaining before? The assessment is the most structured and comprehensive implementation of this life cycle thinking. You can adopt the life cycle thinking also without making a full assessment. You might just have, for example, checklist or a workshop at the beginning of your development, where you try with experts to spot the highest risk, for example. But if you make the life cycle assessment, you are using the most developed tool and the most comprehensive analysis. It's applicable to all dimensions of sustainability. So it's not only environment. You might apply it also to the social and even to the economic dimension. So you might have with one tool all the dimensions except the technical. And you see here the main steps related to, so according to the ISO. What is the role of a technical team? The analysis will always start in defining the goals and the scope of the study. And this is something that actually must be discussed with the technical team. So why do you want to make this analysis? What do you want to see at the end? What do you want to do with this analysis? Do you want to compare to other, maybe to competitive technologies? Do you want to compare options that you have in mind? So this is one key contribution of the technical team. A key aspect of this is also to define what is the function of the system. So when you do a life cycle assessment, you don't compare directly materials or products, you compare functions. So you define what is the function of the system. For example, triggering some light when a chemical concentration is increasing. So it's an abstraction of the real material or real product. And then you need to map the system, so to make a system diagram. And this is, of course, something that the technical team can do much better than any LCA expert, because the technical team knows, at least for their own domain, what happens, what are the raw materials, what are the wastes, what are the energies employed, and so on. So the contribution at this in the first step is really, I would say, is a key, the contribution of the technical team. And then the practitioner, the LCA practitioner, will take this information, and from this, let's say, foreground information with the models and with the database, we'll move to the inventory. And the inventory is really the list of resources that you directly or indirectly took from the environment, from the nature. So if you employ steel, the inventory will be carbon coke, will be iron, will be sand for the concrete that you need for the plant, and so on and so forth. And it will be, I don't know, chromium if you have it. So it really resources from nature and emissions to nature. And from this inventory, again, thanks to models and databases, we define the impact for nature. So depletion of resources or consequences related to emissions. So the ozone hole emissions, also greenhouse gas emissions, different type of pollutions, and so on. So these are the three main steps in an analysis. And you see also from these arrows that they are all correlated. Of course, we start from here, then you move to here, and you try to explain, but at the end you will have probably many iterations to have a real complete and consistent analysis. So I already mentioned the importance of having a clear goal and the scope of the analysis. One of the first steps I would recommend is that this analysis must correlate well with the overall project objectives. So you take here the overall technical or overall objectives in general. You might relate to the taxonomy if you want. You might relate also to other policies if they are more relevant for you. And then you can define what are the impact categories that you want to look at. Again, emissions, or greenhouse gas emissions, the photoreactive ozone formation, the particulate matters, acidification of waters. The list is long, and you should have in mind what is relevant for you. Of course, you also need to assess if you have the data you need. A typical example is you might want to investigate toxicity, but you work maybe with novel or with seldom materials, so the toxicity of these materials is not in itself not known yet. So you need to find another solution, maybe a workaround or some approximation, or you need to stop and say, I cannot model toxicity because I don't have the inputs. So at the end, you end up with this, say, impact categories, which is at the end your indicators for the environmental sustainability. It might happen that some of these categories are in conflict also. So you might improve, I don't know, the emissions, but maybe have a larger material footprint for a certain innovation. So you need to know, to decide what is the priority for you. So you need to have a kind of strategy in these cases. And also important for the analysis is, okay, what do you want to do with these results? Is it only for you, for internal uses? Is it for maybe compare to other technologies, to state of the art? Is it to inform also stakeholders? Which type of stakeholders? All these things will influence maybe not the analysis itself, but the checks that you need to do, the quality or the inputs you have in the report. So it's something you need to clarify. This is a system diagram. So actually there are two system diagrams, because in this system, or in this work, they decided to compare two PCBs. This one on the top is the conventional PCB of FR4 plus copper, and on the bottom is made of paper and printed with silver inks. So this is a high-level system diagram, just to show you one. And you see also that you have different options for the boundaries. So you see here these lines, yeah? In one case, you say it's a life cycle analysis and you have the end of life, but you don't want to follow, say, also the streams of recycled materials. So you have no credits for recycling. On the other side, on the other system, this would be, say, this green one, you decide to follow also these material streams, so you might get also some benefits. So what you decide to include in the system and what is not in the system will also impact the final results. And you see it here, because this is, say, the result also really related to that scheme. These two plots are for the two system boundaries. So in this case is without recycling, and in this case is with recycling, also with the credits. But you can read many more information. You can really learn a lot of things out of these results. For example, they decided to compare, and we saw it in the system, their new technology, this one, to the state of the art, which is this one. And they decided also to compare it not only for one system, but to make different scenarios. In this case, the share of conductive area, so how much of the area is really printed or covered with metal, 10, 25, 50, or 75%. So you have different scenarios. That's the advantage of working with models. You can play a lot with scenarios. It doesn't matter if they're real or not. So you can compare your technology with state of the art. You can compare scenarios. You can compare different systems. And what is very important for technical teams, you see within your domain, within your development, what are the hotspots? What are the main contributions to a given impact? And what can you do to reduce them? One important point is that LCAs, even if they are so, say, scientific and they have a lot of numbers and parameters, they are based on models and they are based on a lot of assumptions. So you cannot compare studies without really investigating what are the conditions behind. What is the system behind? What are the assumptions done? What was neglected? What was considered? What is the reliability of the models used? So it's really difficult to make, let's say, comparisons between different systems. For example, from literature, you need to read carefully. So what happens, for example, in projects where you have a lot of options and you want to compare, and you also want to compare in an early stage different options. This is one example we implemented in a running project where we said, so we established a database, which is actually only, say, a browser-based database where everybody in the team can have access and can input the materials and the processes they are using for their development. Also, all the different options. And also, for example, you can also track the history. So if you change formulation, change the process parameters, it's all there. And from this browser, basically, for this web-based interface, we can export the data and make the analysis, the LCA, in the LCA tool. It's not automatic, but it's a really fast, say, loop here. So I can give in a very short time a fast feedback on technology options that have maybe the same functionality. That could be, for example, silver nanoparticles from different processes. So the partners, the technical teams can really consider in their discussion and in their further development also the environmental impact. And this is a kind of streamlined flow to make it very fast. One last word about circular economy, because the trick here is that, as the name says, it's an economy, and it's not only based on technology. So you need to know also the business model and the context for this material product to be able to evaluate the circularity of this innovation. So what can you do in an R&D project? You usually don't know these things. The point here is in the technical development, you set the boundaries. So you decide if this material or this, say, innovation will be, say, recyclable, will be modular, or will be, say, biodegradable, and so on. So you decide in the R&D stage what are the possible strategies for circular economy later on. So at least at this stage, say in terms of risks, opportunities, you need to consider this. And one last word to the economical context in general, and not only for circular economy, but also for the environmental impact. If you need to model also the use and the end of life, so the waste treatment or recycling, you need to have realistic scenarios for the use and for the end of life. And that means you need to make scenarios that consider, okay, what will be the final product using this material, what will be the fate of this final product, and then end of life. Is it feasible to have a separate stream of materials and to make it really a separate recycling, or will it be part of some other recycling flows? Will we have enough material at all? Will it be dispersed over the whole world, or maybe it's something very local that you might even consider to take back and recycle? So these are not technical considerations in the first place, but they are also important for the LCA in general. And the very last word about the two things: circular economy is an economic model, and it does not lead automatically to more sustainable products. And it's also not part of an LCA by default. But you can calculate it based on an LCA. You can calculate some own indicators, some more KPIs to give you a feeling also for the circularity. The mindset is the same. You need, in both cases, all life cycle stages, and you need the whole system and not only your product. So they are closely related, but they are not the same. And just a few takeaways before I close. Making a sustainable development from the beginning of technology development means you accept complexity and you accept to work and to think in life cycles. And you try to understand what are the consequences of your technology, of your choices on later products. And you might want to understand and to spot quickly the most relevant aspects. So that's all from my side. We have 10 minutes for questions.
Thank you very much for this very nice informative presentation about LCA. That is very important for responsible electronics initiative. Let's check the chat for questions. I can read the question from Tammy. Is LCA thinking assessment being implemented more at the industrial or academic level?
Both. I would say both. So I see it really across all levels. usually the academic world has the issue that they often don't know what happens with innovation, so they cannot really model the potential use stage, or even less the waste stage. On the other side, at the industrial level, they cannot really change much on this product. They can improve, of course, their consumption, but they usually don't develop new materials from scratch. So they have, at both stages it's possible, and they have drawbacks and advantages. Yeah.
Okay, thank you. And there is a second part for the question. Do you believe that transient electronics, biodegradable, bioresorbable, can be a sustainable answer, or would continue to contribute to more electronic waste when taking LCA into account?
That's a very good question, and there is no clear answer. It depends strongly on the application. If you make it biodegradable, it makes sense only if this application, if this product, the full product at the end, can end up in nature or in the organic waste. Yeah, otherwise, there's no real, benefit. Yeah? If it goes in the incineration process, it doesn't make a large difference. So biodegradability is not a solution for all, for sure.
Okay, thank you.
But there might be cases, yeah.
Okay, another question. Thank you for the nice presentation. Recycling is not automatic system. Requires many processes and sometimes complex processes. How to evaluate this type of systems, LCA?
Yes, it's true. Recycling is not always, I'd say, the best option, or I'd say that it is not automatically the best option. It depends on what are the priorities you have. Is it a priority avoiding emissions, or is it a priority recover material because it's important? And it's included in LCA. So all the processes necessary for recycling, from collecting, sorting, treating, separating, and so on, they are all part of LCA. So you have to take this in consideration.
Okay, thank you very much. Is there any other question from the chat? Meantime, I have a quick question about, I'm not an expert on LCA, but I guess there are some available databases that you let's say, collect some inputs. So how much time do you need to perform an LCA report, let's say? And if these databases, you have to pay some license, you have access to these databases. And if yes, what is the cost?
Okay. There are also free databases. So it depends. They are usually specific for certain industries. So you might find also some good sources for free. But of course, the most general and the most comprehensive databases are, say, commercial ones. There is one initiative from the European Commission to make an environmental footprint database that should be open, but it's still, let's say, in progress. So there are some data sets there, and also high quality, but it's growing yet. So it's not good for everything yet. How long it takes for making LCA, it's really extremely different from case to case. It depends on the experience. It depends on the system, on the scenarios you want to see, the complexity of the technology, the level of the database. For print electronics, it's very often the case that the raw materials are not included in the database. So we need to invest time also to model the materials in the first place. So there is no general answer to.
Okay, thank you very much. I think we don't have any time more, but so I would like to thank you again for accepting our invitation to participate in the school. Thank you very much. And
thank you.
Thank you. So now we proceed to the last webinar of the day. I think Hendrik is here. So the last webinar will be given by Dr. Hendrik Sandberg. Dr. Sandberg, can you please share your screen just to check that everything works? I can see him in the chat. Henrik, can you hear us? No response. Let me ask him. He's
Yes, hello. Yeah, Hendrik, sorry, I couldn't get my audio, but now I can hear you, and I hope you can hear me.
Yes. Can you share your screen?
Ah.
You don't need any permission. At the bottom of the screen, there's a button. So let me introduce the speaker in the meantime. So the last webinar today will be given by Dr. Hendrik Sandberg from VTT in Finland. He will speak about advanced printing for sustainable electronics. He will describe the latest advances in the field, focusing on reverse offset printing. I think it's the state-of-the-art printing technology that using it, you can scale down the printing features. And he will describe some device applications using this technology. A few words about Dr. Sandberg. He's a principal scientist at VTT, Center for Printable and Hybrid Functionalities in Finland. He has a PhD in physics from University in Finland. His work is currently focused on printed electronic devices and circuits, polymer device physics, printing technology and printing information, as well as heterogeneous and monolithic integration for flexible electronics. He specializes in device and circuit development towards sustainable solution, as well as the development of analog printing compatible processing techniques from the lab scale to the roll-to-roll pilot scale, and on related in development, in particular, the topics of thin film polymer transistors and circuits, organic photovoltaics, and graphene applications. So, you already share your screen, so this is perfect. So thank you very much for you accepted to participate in our school. The floor is yours. Thank you very much.
Yes, thank you very much for your kind introduction, and also thank you for inviting me to this series. And yeah, you already mentioned about my topic and me, so I will go straight to the next slide. So VTT is a technical research center. We work in between academia and the industry, and we focus on the Finnish industry and the Finnish markets, but we also work on a very global arena, as of course everyone nowadays. And the goal original for VTT is to increase the global competitiveness of Finnish companies. So we are about 2,000 people. In VTT, a little bit more. Most of them are in Espoo, in southern Finland, close to Helsinki, and that's also where I'm also located myself. Then we have other locations in Oulu and Tampere, which are also fairly large, and then a few more small offices. When it comes to printed electronics, much of the upscaling is done in Oulu, which is in the north of Finland. And that's where we have roll-to-roll printing lines. And a lot of different processes related to the upscaling of printed electronics and related technologies. VTT is established in 1940s, so it's already a rather old institute in Finland. So first I will begin with some perspectives on the sustainability and the different opportunities that this brings to both flexible electronics and in particular printed electronics, because this is a central motivation for what we do at VTT. So we are at the moment in the middle of a digital transition, and this is really a worldwide process that's going on. This means there will be a lot of electronics. It all relies on electronic gadgets and also the large systems, of course, that drive this this whole digital environment. So a lot of devices means a lot of waste as well. So the electronic waste is increasing really, really rapidly, and we see only at the moment about 1/5 of the waste being recycled or collected even. Even in EU, which has quite a lot of legislation in this area, only collect about 40% or a bit less. So this is a big challenge to somehow manage this extreme increase of devices, and then in the next step, the increase of waste. This also consumes a lot of materials, both raw materials and materials for energy generation to drive all these processes. And many of the materials that are required for electronics are quite scarce, or they are difficult or expensive to extract, or they come from conflict areas. And yeah, there are many challenges related to this transition that's going on, but there is no reason to think that it would not continue. So we have to address the problems. So there are many global frameworks to tackle the challenges related, and one, of course, overarching is the United Nations Sustainability Development Goals. So these cover all the major challenges globally, not only technological, but also social, and of course, environmental. And it has to do with many of the trends, the ones often called megatrends going on in the world at the moment. So in our work, we want to relate all our activities to addressing some of those development goals. On the European scale, we have also many different agendas. And for example, we have this Green Deal that's about combating the climate change effects on the European market or the European scale. And of course, this is very much directly related to the sustainability. Then we have, for example, the Eco-Design Directive from 2009, which is already being a bit old, and it's being replaced. So there is a proposal already which is being developed, which is focusing not only on the eco-design, but also on the sustainable products regulation. So this is something that's being developed, and there are many aspects to this, but one, for example, is the digital product passport, which is also one of the focus areas where VTT is active now in the printed electronics area. Then we also have the European Chips Act, which is a big initiative as well. The target here is to support the European digital transition, but not only that, not only to make Europe more resilient or competitive in this area, but also to address the sustainability aspects of the IC area as a whole. So this is setting the stage more or less for all of the activities that we do in this area. The sustainability technology, you have to watch from different angles. So first you have the design of the product, and this is actually where most of the impact on for example, environment is determined. Even let's say if a product is poorly designed from a sustainability perspective, it can be very difficult or even impossible to compensate for these effects with other actions. So the design is really important. So we want to strive for more modular products, because that will enable further processing or further addressing the sustainability issues. So just as an example, we have different smart labels developed, which are autonomous when it comes to energy. They harvest from light or RF and so on. And these consist of quite clear modules that can be extracted and reused. Then we have the material part. There, avoid, first of all, scarce materials in the raw materials, and also, of course, conflict materials, and really strive for using abundant raw materials with a low environmental impact. And also reuse other materials that come out of other processes. Then we have the energy management in both the processes and also in the process for manufacturing both materials and devices, and also when it comes to the management of energy of the actual device. So printing is a very good method to lower the energy demand as a whole, and especially additive manufacturing methods are proven to be efficient compared to much of the current technology when it comes to the energy resources management. Also, miniaturizing and integrating more monolithically into devices helps in this respect. And then, of course, while using devices and disposing them, really have to take care of the sustainability aspects of the product, and try to target really a circular economy, in the sense that nothing is really discarded or end up on a dump as such. So reuse modules, take them into the design phase, reuse those, reuse materials, collect them and feed them into the materials development. Some materials cannot be used in that way, but they can be used to generate heat for the energy production and so on. This all helps a lot, both from the environmental and economical aspects. Now, if you look at no problem. If you look at the end of life of these devices, of course, separating materials is important. And for this, we need to know what's in there. So this digital product passport is one initiative which strives to collect data on everything that goes into a product, so that you can use it later when you dispose of the product in the end of the product's life. And then you get various waste types and grades, which has to be addressed separately. And then, of course, focus on the reuse, repurpose, recycling. These are really important aspects of sustainability of electronics and sustainability of any process, actually. We are involved in many of those initiatives. I'll just mention one here, which is the Astronics project. There are a lot of partners there, 46 partners from 11 countries, and it's coordinated by Philips. This is just one example, just to show the large range of aspects that has to be addressed. I wanted to use some time to look into this to set the stage, because as the sustainability perspective is driving VTT's activities a lot, also in the printed electronics. This is the way we choose what to develop, what to focus on, and what are our priorities. I will now focus on the third of these sustainability perspectives, which is the sustainable materials and manufacturing methods. And there we have developed some techniques, and we use a lot of the most common printing techniques as well. As mentioned, the printing as a manufacturing method is proved to be very efficient when it comes to the use of energy, for example, but also used of many other materials. Additive processes in general are more sustainable than other methods. Many of the current methods are not additive methods. Then we also want to reduce dimensions, reduce weight, and heighten the integration level. All of this can be done for many applications with the printed electronics technologies. And printing is also compatible with many renewable raw materials and substrates materials, and we can use mild solvents. Many of the printing processes required also for electronics actually can use aqueous solutions. If we look as an example, just a printed circuit board, the conventional process relying on FR4 and etched copper, if you use that as a reference, just by changing the etching process of copper by printing silver nanoparticles, we can halve the global warming potential. And if we also get rid of the FR4 and use a very common plastic film like PET as a substrate, we further decrease this potential by down to 1/3 of the silver nanoparticle on FR4. So these are really huge differences. Then we can move away from PET, which is not the best environmental substrate, to paper or something like that. But that will not change this global warming potential much, but it has many other benefits, of course. And so this is like the first step, to look into the substrate material if we want to increase the sustainability of a device or of an application. Moving into more sustainable materials doesn't necessarily mean you are compromising on the performance, which is important to note as well. For example, if you want to move away from PET and find a bio-based film, for example, to use as a flexible substrate, you can actually, by generating the optimal material and the optimal surface, you can increase the properties of the printed electronics on top. So when you develop everything together, you can often reach, let's say, improved results compared to just making incremental changes. And one target, except for reuse and repurposing, is just to be able to for example, be able to waste dump things in a way that that will not leave any traces. So leave no trace is a good principle also in electronics. And for example, the substrate, which is the most bulky part of a device, usually of an electronic thin film system or flexible device, if that is biodegradable, very little material will be left. And that can often be collected as well. For example, in this example here, only in a few weeks, the substrate is degraded in a way that is environmentally friendly, and you can separate the metals and the chips or other packaged components from this material. Of course, we all know that silver is not the optimal material for the environment, and if you have solved the substrate aspect, then it's important to look into the electronic materials first, the conducting material, because that is also in fairly large amounts compared to many of the active materials or separate components in a flexible electronics device. So if you do the LCA of printed electronics device, you will see that the printed silver is a main contributor to the let's say the poor results. In this case, we have looked into the CO2 equivalent of different solutions for the same device, and there you see that changing substrates between PET and bio substrates doesn't change too much. But when you change the silver ink into even a copper ink, which is another metal, you see a huge decrease in the CO2 levels, down to 1/5 of the silver version. And then if you can go away from metals altogether, most often you can also see a further reduction. Of course, it's important to keep in mind here that the conductivity of different materials will not be the same. So with copper, you can often reach similar electronic conductivity levels as for silver, but going to carbon or carbon-based conductors will see a decrease. So you have to do some wise choices there. Maybe use carbon-based inks for areas where you can have large areas to reach the required conductivity, and then you can use metal-based inks where you need, for example, fine features, narrow lines, and or a really high conductivity. So going into the printing method itself, at VTT we have used a lot of standard printing methods to realize, let's say, conductors, antennas. This is very common, and it's done in many labs, of course, and many companies. But there are very few techniques to make really small features with a consistent and high electronic performance. And there we have been focusing on one method to reach really high resolution, as well as registration accuracy of printed conductors, but also other materials required for integrated components. So we call it reverse offset printing, and it's a high resolution printing method which is compatible with many different materials, which can be used to make a lot of different applications or functionalities. transistors, for example, but a lot of different sensors as well. Grids, transparent conducting grids, and so on. The sustainability aspect of this method is similar to let's say other printing methods, and it's a very unique system, especially in Europe. And we can print metals, metal oxides, and polymers, for example, for insulating layers. We can reach even below micrometer accuracy, and also the overlay alignment is on the same level. Yeah, that is just an example of a transparent metal mesh using silver on PET. So really fine lines, and the applications then can be anything where you need this kind of features. So if we look at why we need this kind of printing, if we look at most of the printing methods that have been in use for a long time, they target quite thick layers of material, or they enable quite thick layers, and the spatial resolution is quite high. So for example, the screen printing method, which is mostly used, for example, to print carbon conductors, makes quite thick films up to 10 micrometers, and in the millimeter scale, or down to maybe 100 micrometer, both sides of 100 micrometer. And then we have other methods like flexographic, which is slightly lower in both respects. There are different inkjet systems, very specialized inkjets as well, which can make very thin layers and also quite small features. But still there is a lower limit also for these dispensing methods. Again, can make quite thick films, but they don't have the spatial resolution. And then of course there are a range of coating techniques as well. With the reverse offsets, because we can go down to micrometer scale and also thickness below micrometer, we can make many devices, and the TFT, the thin film transistor, is one of the best model devices to test both materials and methods to optimize the process as a whole, because the TFT is really sensitive to differences in thickness, differences in spatial dimensions, and differences in surface properties. So it's a very good model system in that sense, and it's important to be able to do the high resolution patterning to be able to have a higher integration level in electronics. And the higher integration level also lowers the yield problem, which is often an issue with printed electronics. There's also a very good overlay accuracy in this device, which means we can minimize the parasitic properties of a TFT, which is the overlap between the gate electrode and the source drain electrodes. And all this can be measured also in the electronic properties of the device. So it's a very good testing device. So we can reduce the device size, for example, down to a reasonable display resolution, which is required in modern devices. And we can increase the yield, and by that also increase the complexity of the circuits. And then also we can increase many of the operational features of a device. So more details about the process as such. it has, as the name suggests, it has several steps. So it's an offset type printing method. So first we apply a continuous film of our material, our ink, in the coating step. This is coated onto a cylinder with a PDMS film on top, and the properties of the PDMS film is very strict. So it has to have exactly the required properties, and we also make these PDMS films to work together with the ink and the coating process. Then the fully coated PDMS cylinder goes over a cliché, which is a patterned layer. In our case, it has a relief pattern. It can be a metal film, it can be a silicon wafer or glass wafer of some kind, but it has this height differences in the surface, and with this you remove all the material which touches the surface of the cliché, and then that's the off step. So you remove some material, and then after that comes the set step, when you apply the material which is on the roll onto your substrate, which is then usually a flexible substrate. So we use a capillary coating system for the PDMS coating, and this requires low viscosity and surface tension of the ink, and the ink optimization, of course, is also important. And we don't do that too much in-house alone, but we do it together with partners. The ink has to remain in a semi-dry state on the cylinder, so that's why the PDMS properties is important, because some of the solvent is absorbed into the cylinder or into the PDMS film, and some is of course evaporated, and that semi-dry state has to be stable for some time, so that this off process happens reliably. So the ink you want to remove in the off step is left on the cliché, so the cliché has to be cleaned before the next process. Then you have the ink still on the PDMS, still in a semi-dry state, so that it can be transferred onto the substrate. And this is where you just press the cylinder onto the flexible film, and it will transfer due to the interaction between the PDMS and the ink, and the ink and the substrate. So that's in general how the process works, and you can do a lot of things then with this process. For example, we have demonstrated these TFTs, for example, using metal oxide semiconductors. We have made various kinds of grids. We also printed resist patterns. We have printed different antenna structures, absorbers, and so on. Those with the boxes we have made in-house, and then we also include some example of what has been done elsewhere. And many of the institutes or companies using this method are interested in the display technology. So we have, for example, Sony and Samsung involved quite a lot. And in general, we can say that this technique is used more in Japan and South Korea than in, for example, Europe and the US. This is how the system looks in practice. So we have the cylinder in the middle, which is stationary. There we attach the PDMS onto the roller, and we have the glass slit holder beside to handle the coating when the cylinder is rotated And then we have the cliché stage on the left and the substrate stage on the right. So these travel on the same translational stage beneath the PDMS cylinder. So in the first step, the cliché stage moves beneath the roller and removes the material we want to remove from the PDMS. And then in the set stage, the other stage moves under the roller in the same way. And there are camera systems in both stages to make sure that the accuracy or the positional accuracy is what we require. Of course, if you do very small structures, also very high positional accuracy is required in this device. So as mentioned, we can reach a sub-micrometer resolution and also a similar positional accuracy. Then the layer thickness is low because we apply a very thin layer of this material onto the roller. And the line edge definition is also on a very high level in this method, which is one of the big advantages. And if we look into the edge definition of many other methods, printed methods, for example, we see that there are all kinds of issues with most of the printed electronics additive methods, but the reverse offset, which is on the right, actually reaches a very similar edge definition quality as photolithography. So this also means that we can, by printing, target similar applications as currently require photolithography. I mentioned the overlay accuracy or the registration accuracy in this device. This has been optimized in several projects as well to reach as high as possible, so that it's actually on the same level as the printing resolution. Otherwise, it doesn't make much sense. But as you can see from the results, it's on a high level, and we see an error in the micrometer range maximum for a large number of samples over the full printing area. It's 10 by 10 centimeters in this case. Our machine can handle up to, I think it's a little bit more than 200 times 200 millimeters. But the quality, due to the process design, it's very uniform over the whole area. This, of course, requires also very stable substrate material. So this is actually often one of the drawbacks, that the method is much more accurate than the stability of the substrate. So much of our work is now done on polyimide films, which are very stable, but we also do a lot on PET. But mostly we work on a few micrometer scale, not on the absolute minimum of the accuracy of the method. And this test is really done in the authentic way, that we print one layer, remove the substrate, and replace it on the stage again, do the positioning, and make a second print. So it's not consecutive prints without touching the substrate. It's really a measure of how accurately you can print onto another layer. What are the materials here? As mentioned, we have this PDMS, which we have to optimize and develop, and then the inks. And the viscosity must be low. and it has to have the optimal wetting properties on PDMS. It should reach this semi-dry state, and it has to maintain this state for a sufficient time. And the reason, it also has to have the sufficient cohesion to make the transfer from the PDMS as clean as possible, both onto the cliché and onto the substrate. And the semi-dry state now in our system is for more than 1 minute, so it's plenty of time to do the whole process under, let's say, stable conditions or continuous conditions. And as you can understand, the coating thickness uniformity is key to this whole process working. There are various inks available, but to be applicable in more devices or applications, more inks should be developed. Currently we use silver and we have some copper inks as well. And then we have some semiconductor material based on both organic molecules and also on metal oxides. And then there are polymers you can print with this method. So we see this as a good way forward to reach high quality electronics by printing. If we don't have a suitable ink, we can always do patterning with this method, and that is the last part I will talk about with this method, that you print a pattern, and then with a material that works well with the process, and then you apply the material you want patterned, and then you do a lift-off process. Well, actually, I had some examples here as well before I go forward. This is just examples of a metal mesh and a landing pattern. Yeah, this is an example of the TFT stack. I will go quite quickly through this because I see that time is running. But we have demonstrated, as mentioned, TFTs. And for this, we use silver material for the electrodes. And then also what is challenging is that we need to keep in mind that we are doing multi-layer structure. So we have to both think of the solubility in the solvent and the solvents for the various inks, and also the temperature or the thermal budget limitations. For the development phase, we also combined it with different lithographic steps to be able to really isolate the step or the manufacturing step which is being developed. So now we see the resist patterning, and the motivation for this really is that there are not so many materials available in ink form which are suitable for this method currently. So to be able to widen this spectrum of material, you can do this resist patterning. You can then apply another layer from solution, or you can do it in a vacuum deposition. And this, of course, widens the range of applications at this stage of the development. The target, of course, being that we would have all the required materials available in ink form so that we can print them directly in an additive process. So FlexRad is a project where we develop this lift-off process in particular. And there you do the printing of a pattern as normal in the lift-up. Then you apply a coating, and then you do the lift-off process. And with this, we can also reach similar accuracies, even down to submicrometer dimensions of thin lines. And with this, we have been able to do devices, TFT devices with metal oxide semiconductors, which require, for example, aluminum as the source and drain electrodes. And for this, there are much more materials if we rely on the vacuum deposition of metals. And these are just examples of what we have done. And this is more details on the TFT device. And as time is up, I will skip forward with the summary. And as mentioned, the reverse offset printing is a scalable print pattern method, and it can reach the levels in patterning resolution which are required by current electronics industry. So this is the most important takeaway from this method. We have a process on the 8-inch scale with a high accuracy camera system to also allow alignment accuracy of on the micrometer scale. We combine this also with many other printing methods and other processing methods. We have demonstrated many different devices, of which the thin film transistor is the model device, because that also tells us a lot about how the ink works, how the material works, and how the process works. And with this, we can make circuits and systems. And we are targeting mainly flexible electronics for wearables, for example, with some sensing elements. So we are still, of course, in quite simple devices, but we are more in the domain where currently integrated silicon circuits have been required. So the next step is really to work on continuous work on optimizing the process, but also together with partners develop more and more materials. The sustainability aspect of this method is that we can do additive on very thin or on flexible substrates in very thin layers. So the amount of silver, for example, if we use silver ink, is really small. So that also helps very much if you look at the sustainability budget. And sustainability challenges do require immediate actions. So that is why we focus on this area. And there are big challenges that we are facing at the moment. So we hope to work together with partners to progress this method and many of our other flexible and printed electronics methods in VTT. Last, I will acknowledge the people working on the reverse offset printing in particular. Much of that is led by Jaakko Leppäniemi, my colleague, and we have a team involved in various parts of this process development and application development. We have funding from Academy of Finland and many EU projects. And last, I want to acknowledge also the VTT team, my supervisor or the team leader, Maria Smolander, and Lisa Hakkola is our expert on sustainability actions. And last, I want to thank you for your attention, and I'm happy to answer any questions that you might have.
Thank you very much, Kevin, for this very nice presentation. Fantastic results in your group. There are some questions already in the chat. Let me go there. So one applicant asks about, so considering that copper and carbon possess greater potential compared to silver, what are the primary obstacles hindering the application of this space containing either copper or graphene or carbon-based materials?
Sorry,
why are not replacing silver with other base containing either copper or carbon?
Yeah, so yeah, as I mentioned, we do most of the work with silver, and as in most of the printed electronics software, silver works very well. So it also works in this method very well. So when we want to develop the method itself, it's good to work with a material system that is stable and also very functional. We do work with the copper inks that are available from other partners or even commercially. The challenge with copper is that it behaves differently on the substrates that we use. Even on polyimide, it behaves differently than copper. So we need other sintering methods for copper compared to silver. So in practice, this means that the heat generation in the printed copper layer, even if it's as thin as the silver layer, it generates more heat, and that affects the surface of the substrate. So what we do with the copper in particular is focusing on the sintering process, not on the printing process. So we focus on the surface of the substrate, and that is more or less what we can do. And yeah, and the actual sintering process, we focus on photonic sintering for this, because the thermal sintering is more tedious, it takes more energy, and also it affects the substrate more. Yeah, sorry.
There's a continuation of the question. Is there any stability issue related to copper?
Well, if it's entirely sintered, the copper, it is very stable. Yeah, I mean it's a continuous copper layer, but of course it's still in the 100 nanometer to 100 nanometer maximum thickness range. So you have to shield it from oxidization somehow, as you also usually do with silver if you print that in a very thin layer. But currently the challenges with the copper is in the sintering and the optimal interaction between substrate and copper during the sintering process. So we haven't been able to really look on the time scale how the copper compares with silver. When it comes to carbon, you mentioned carbon as well. There have been some tests with carbon. Yeah, graphene in this case. There are not too many people developing carbon-based or graphene particle-based inks with the properties that is compatible with this method. So we have not been able to do too much on that. However, it will be a very thin layer also in this case. And we expect that, as with other printing methods, you require quite a lot of even the particulate graphene inks to be able to reach the level of conductivity you need. But this is definitely one area which we are very interested in. So we are looking for people that are interested to collaborate in the ink development for various materials, including graphene, and definitely graphene is one of the most interesting from the sustainability perspective. But that mentioned also, copper actually has fairly good sustainability profile, so it's not at all a bad option.
Okay, thank you very much. Also, they ask about what is the throughput of the rope system.
Well, this of course is a development device. It's a research instrument. So let's say the full printing process from coating the PDMS to when you have a printed substrate, that currently takes maybe 1 or 2 minutes, and then you have to do the sintering. In our case, we can't do the sintering in that actual printing device. We transfer it to another system where we do the sintering. Let's say the web speed, if you can compare it to some value for web speed, of course it's quite low in this kind of device. I don't have any idea of challenges related to optimizing the speed of this printing process. I know there are companies, for example, in Japan developing this method as well for upscale processing, and I'm not aware of the specifications for those systems. It's not public information.
Okay, thank you. Is there any limitation regarding the substrate?
Thank you, Professor.
It was Mr. Saman Terry that asked before. So is there any limitation regarding the substrate that we have to use for the rope?
Well, the limitation has to do with the surface quality, in the sense it has to be flat and also stable, let's say, in the plane. Otherwise you cannot do, for example, consecutive printing on this accuracy level. So even with the PET, we see that after some processing, the rigidity of the sample in the plane is not always enough to be able to print many layers which are this accurate in position. So we need to have stabilized and optimized substrates. Then when it comes to different materials in the substrate, that depends entirely on the ink as well, because you transfer the ink in a semi-dry state, so it has certain properties. So you also have to check that you can get the transfer to the surface. But that can probably be addressed with the surface treatments or even coatings on the substrate.
Okay, thank you. Another question from Tammy Lewin. As rope is limited to low viscosity inks, I suppose this means that the deposit film will also have low thickness.
Yes, it's also, yeah, sorry.
But perhaps affecting the overall conductivity. Is it possible to do multiple coating steps?
Yeah, this method will result in quite thin films, because otherwise you will lose the benefit of this method, because if you apply a several micrometer film by transfer where the features are sub-micrometer, you don't have that control of you can't transfer that thick layers in that small dimensions. But you can, of course, do multiple printings, because the accuracy of the consecutive prints is the same, on the same level as the print pattern accuracy. So that's what we would do. But that said, the conductivity of the silver layer or the copper layer is quite good, even though it's on the 100 nanometer or 150 nanometer thickness scale. So the internal quality of the layer is good in the metal film in this case. And probably this has to do with the fact that sintering these thin layers is uniform and efficient, because the layers are so thin.
Okay, there are quite a few questions more, but let's do a last one, because we don't have the time. Thank you a lot, Professor Sandberg. Can we reach semi-transparent electrodes? I mean, or which technique is the best one to fabricate semi-transparent electrodes, if I understood well?
Well, currently I showed some pictures of metal grids. These have so thin lines that if you have a grid with very thin silver lines, it will in effect be both conductive and transparent. But then it depends on the optical properties required of this transparent conductor. But I think there are similar challenges with any transparent conductor, that for example the haze will be affected and so on. But that is the current way to address this transparent conductor problem, that you make grids with very fine lines, and that means they are effect transparent, even though the conductivity is based on a metal layer or metal grid.
Okay, thank you very much. I think this with this we close the session today. It was the last webinar. Thank you very much, Hendrik, for your participation, and all the audience for the attendance. So we're waiting for you tomorrow at 11 o'clock as always. Thank you very much. Have a nice night. Bye-bye.
Yeah, you too. Bye-bye.
Bye-bye.